All right. So happy New Year. I hope that you all had a great start to the year, and yeah, just happy best wishes. I hope that you have a very successful 2026. You're able to accomplish big goals and so on. For this video, we are going to talk about formal methods, which is a recurring theme in our videos. Specifically today, we are going to discuss using TLA Plus for the formal verification of concurrent and distributed systems. So first, we are going to start by kind of just introducing the why of formal methods and, formal verification. So concurrent systems and distributed systems they are complex, right? And the reason for the complexity is usually down to different things. So we have scalability, performance, fault tolerance, security, and also just the cost, right? Because you can have a solution or a system that you design and then you deploy it and it basically bankrupts you. So you also have to watch out for costs, which sometimes gets somewhat relegated to the background as people are building these systems. Where it's like, oh, just build it so that it works and then just deploy it. And sometimes there's no particular attention paid to cost or how to write things efficiently enough that you can minimize cost. But that's, that can be a whole separate topic itself. But really, the complexity comes from trying to balance requirements across all these different axes. When it comes to designing systems, there are really two things, principles and the properties, right? Principles are more like non-functional requirements. You don't necessarily have explicit ways to check this directly in your program, but for the system as a whole, when you think about the way it's supposed to behave, there are certain principles, right, or non-functional requirements that we expect. You will say things like you want the system to self-heal, you want the system to be elastic, right, to be stateless. Recently, with the whole idea of durable execution or durable workflows, you want the idea of things, your system being stateless to some degree and having pause and resume semantics. And it tends to be that for these principles or non-functional requirements, while you cannot explicitly put it down to very specific algorithms or patterns in the actual code implementation, you can observe that those principles are non-functional requirements via telemetry, via some sort of, monitoring of the system. So besides principles, we have properties, and properties really, they're the functional requirements of your system. And those are things that you can actually pretty readily identify by specifically checking them or asserting them in the code itself, the implementation details. So you will say things like you want to make sure that all the data that is committed as failures, right? There should only be one leader per term. This is relating to leader election. You don't want to have a split brain problem where due to some sort of network partition, you end up in a scenario where the system can have two or, more than one leader at a time, which obviously is bad. And so with TLA Plus, we can focus on modeling and really formulating and formalizing the intent of your the properties of the system. We can really focus on that aspect of things. So when it comes to verifying systems, there really are two approaches. You can go with formal proofs, or you can go with model checking. The thing about formal proofs, it involves math, lots of rigorous math, because you're trying to prove you're trying to prove correctness for all possible executions. It's extremely time consuming, both in terms of just hours, right, that needs to be invested. And it's actually, based on my understanding, I haven't done formal proofs professionally, but my understanding based on what I've read is that it's the actual formalization of the thing that you're trying to prove, that can actually be, to some degree, the hardest part, because you really need to understand how the system is supposed to behave in order to formalize that expected behavior. So besides formal proofs, right, you can go with model checking. And that is the approach that, that a tool like TLA Plus is useful. Compared to formal proofs, it's a more practical and accessible way to do formal verifications. It's more of a brute force approach compared to formal proofs. And so you have to be careful because the way it's searching for faults, or, it's exploring different execution paths, which are called behaviors. It does so in a breadth-first search way. And you have to be careful to make sure that you don't end up, the way you do your specification, you don't end up having to deal with an infinite state space where basically the model checker has to search an infinite state space, excuse me. Yeah, and TLA Plus is one of the most powerful model checkers available. So in part 2, let's talk about TLA Plus fundamentals. So with modeling, you want to definitely focus more on the what rather than the how, right? It's really about thinking above the code. It's very important that you focus on describing the behavior of your system. You need to pick and choose the level of abstraction that you'll be going with as you're modeling the system. You have to be careful not to get too bogged down by details, which can be a sign that you're focusing too much on actual implementation details. You really want to think about the abstraction of it all. You don't want to go too fine-grained, right? You don't want to model every TCP packet, right? If you're trying to model the TCP protocol, you don't want to track every memory allocation. But then again, you also don't want to be too vague. It's about finding that sweet spot of abstraction. You want to capture essential semantics of your system. You want to consider enough details to find bugs, and be careful that you don't end up in a situation where your spec is so detailed that it basically yields an infinite state space in terms of, the model having to explore execution paths. Moving on to how TLA Plus allows us to specify our systems. There are really 3 building blocks. We have constants. These are immutable, statically defined aspects of your system. You have variables, which again should be self-explanatory. They are the mutable values during lifetime of the system. And actions are ways in which we are able to modify the state of our system. When we write a TLA Plus spec, we are essentially describing a state machine. And with a state machine, you always want to have an initial state. So one thing to keep in mind when we say initial state, it doesn't have to be a very particular state of the system. Depending on the system, there might be really only one possible initial state, but that's not always true. Actions are the way in which you are able to transition to modify your variables. So you will go from the initial state S0 to the next state S1, and then to the next one X2, and so on. And the important part about your spec is that you need to definitely think about your invariants. You have your safety properties. You want to think about the bad things that should never happen, right? You're trying to make it so that you can be sure about the fact that a particular set of things must be true always. An example of that would be you can only have one leader per term if you're thinking in terms of the Raft algorithm, the consensus protocol. All committed writes are durable. So in terms of coming up with these properties as you're trying to model your system, it tends to be the case that your safety properties are easier to come up with, right? It's easier to really point to things where you feel very confident about the fact that, okay, yeah, this thing right here, this should never happen. With liveness properties, it can be a little tricky sometimes, right? especially relating to picking the right level of abstraction with the way you specify your constants and your variables and what that means for the state space and the exploration of different possible execution paths, right? It can be challenging to come up with your liveness properties. And the way to remember liveness properties is, you want good things to eventually happen. If you think about a scheduler, right, you want a liveness property. There is the scheduler eventually schedules a job, right? If there is a job, right? Assuming the assumption here is that there will be a job posted at some point and it needs to be completed. The job needs to run and be completed. So you want a scheduler that eventually schedules jobs, right? Because that's its job. It's a scheduler. Other examples, every request eventually gets a response. Even if it's a failure response, the system eventually elects a leader, right? There are consensus protocols that are leaderless protocols, but if we were talking about something like view stem replications or the Raft protocol, you gotta have a leader. And so your system eventually needs to elect a leader. Otherwise, what's the fucking point, right? Messages eventually get delivered. I think we can all make sense of that one. Okay. So the trade-off between model checking and, using formal proofs. With model checking, it's a brute force approach. You want to be careful with how, again, you pick your constants and variables, because then that affects your state space and your model checker at some point. If there's too much to explore, it's just gonna basically crap itself. Proof assistance takes a long time, requires a lot of effort. You should really only reach for that if you have the resources. From a practical standpoint, for most engineers today and the systems that they work on, right, going with model checking is probably preferable. Again, pick the right constants, pick the right variables. Anything else we want to specify here? Not really. I think the message is kind of clear. In fact, especially if you just kind of trying to fill things out, right? Always start with a limited set of constants and variables and try to resist the temptation to think in terms of implementation details. Take a step back, think about the system, and pick the right level of abstraction. Let's go to the example TLA snippet. We can quickly prototype a simple message passing the set of messages that are exchanged. While it's the messages that are sent, we'll see why I'm being specific about that, and the set of messages that are received. Initially, both are empty. The sets of messages that are sent and received are empty. And so then we have two actions, and those are parameterized action. Well, in the case of sending a message, the action to send a message, we have a sender, a receiver, and the message itself as parameters. And so what this says is that the new set of message sent will be basically the existing set of messages combined with, this new message where, we set the sender and we set the receiver and the body, which is the message. And that last line here that says unchanged received, it's a way to specify basically that a given action in TLA Plus don't have to update every single variable. And then we have the other action, the receive message action. It's saying that there is a message in a set of messages sent such that that message is addressed to this particular receiver. Once we have landed on such a message, or we find such a message, that we update the set of received messages. So you can think of that as being the acknowledgement of having received the message. And so we update the set of received messages, but we also update the set of send messages, right? So it's basically like pulling a message from a queue and then sending an acknowledgement that the message was received and processed. Looking at another snippet, specifically in this case for leader election, we can look at an invariant of a leader election protocol. And really, to get right down to it, right, the invariant really is that it's a leader election protocol, and so there can really only be one leader at any given point. And the way we express that here is that we say for any two nodes in the cluster, if whatever node 1 believes to be the leader and whatever node 2 believes to be the leader needs to be the same, given that they are in the same term. Essentially, what we're trying to prevent here is that we don't end up with a split brain situation. Okay, so temporal properties, specifically in this snippet, we're saying for all pairs of nodes N1 and N2 in the set of nodes, we want them to agree on what is the state of the database. And so those symbols, I added descriptions for the symbols. So the square brackets, right? That means always. And then you have the turbo, is that what it's called? Turbofish? Where did I get that from? Rust? Anyway, whatever you will call this, that means eventually, right? And so you can have eventually always or always eventually. Right, so always eventually means that the thing that needs to be true can happen repeatedly. It can become true repeatedly. So there may be, throughout the lifetime of the system, but there may be moments where the assertion of the property is not true. But the point is that from a liveness perspective, eventually it will be true. It might stop being true, but then it will eventually also be true. You can also make the case for eventually always. In that case, what you're really saying is that your system goes along, it's doing its thing, right? It's having fun or not because things are going wrong, whatever. It's not in a state where you can say that things are quote unquote stable. But eventually always says, eventually, something's gonna happen, or a value will be set. Something's gonna happen, or a value will be set. Once that happens, it must stay that way. I think one thing that just came to mind is that in Rust, for example, I think there is what is it called? Lazy static. And in terms of semantics, the idea is that you want something that will be constant, but you also don't necessarily have the value itself initially, but once you do, it stays that way. So lazy static, it will be lazily statically set. So that would be a good example for eventually always, I believe. Real world impact. Amazon is definitely one of the more, in terms of big corporations out there that actually invest resources in formal methods. Amazon is one of them. They're really big on it. And as one will expect, one place where it will be very beneficial is with applying formal methods to a service like S3. Because S3 is like, I think Jeff Bezos, the way he pitched it, I think allegedly, is that he wanted malloc, the memory allocator in C. He wanted malloc, but for the cloud, basically. And I think based on how widely used S3 is these days, not just, Amazon S3 itself, but also just the protocol, the S3 protocol, how prevalent it is today. I think, we can say that that was a successful project. So yeah, Amazon uses formal methods extensively. They've written papers about how it's been very useful to them and helped them solve problems that would have been almost impossible to, well, according to them, I don't know, almost impossible for them to detect without the use of formal methods. They've been able to discover bugs in production. Another big giant in formal methods is Microsoft. Besides Microsoft, you also have MongoDB. I don't know why that jumped into my head right away, but I think it's because I was saying Cosmos DB, and it's one of those NoSQL databases, MongoDB being one of them as well. So again, TLA Plus, very, very widely adopted tool for companies that make use of formal methods. So when should you use TLA Plus? I think up to now, I think I've said the word distributed consensus quite often. If you wanted to really understand how Raft, the protocol works, or Paxos, the ViewStamp replication protocol, instead of just staring at code implementation, you could do yourself a favor and actually look at the TLA Plus spec. That's a really good way to get familiar with those protocols. You can also do it. It doesn't have to be for big systems, by the way. You can also use TLA Plus to really understand concurrent data structures as well. If you're just writing a typical CRUD web app, you probably don't need to mess with TLA Plus for that. All right. So what we covered, we first talked about form of specification from a general standpoint. Why should you care? The fact that distributed systems, concurrent systems are complex. The complexity is down to different competing needs across different axes. You have matters of performance, matters of scalability, fault tolerance, security, cost. You have to somehow mix it all up and produce something that works reliably. You want to think in terms of the functional versus non-functional requirements of your system. You have the choice between model checking and formal proofs. Formal proofs being way more challenging work that you will do for verifying your system. Model checking will be a more practical and approachable, at least even to get started with, even if the goal is to eventually have formal proofs. Maybe a good start will be going with model checking. We did a brief, definitely very, very, very gentle introduction to TLA Plus with, the concept of constants, variables, actions, how we think about state machines using TLA, and the fact that you want to find the right abstraction, because too many details, you risk thinking too much about the implementation details of it all, and that can create issues in terms of actually checking the model, because the model has to explore all execution paths based on the constant variables and action that you specify. And in part 3, we talked about the idea of safety versus liveness of your system. Safety is when you want to ensure that bad things do not happen. With liveness, you want to ensure that, good things eventually happen. So the TLA Plus mindset, start thinking in code, start thinking in state. I believe it's Leslie Lamport who said, the creator of TLA Plus, he has an expression that I think is very relevant, especially with the advent of all these AI coding agents. He says, programming is not coding. And his whole thing is programming really requires thinking about your system. Really thinking and programming your system is important. And that does not necessarily mean coding. So yeah, think in states, right? What are all the possible states? Think about the transitions of your system, going from one state to the other. You want to think about the properties, what must never happen, what must eventually happen. And yeah, so you want to focus on modeling the what versus the how. And it's not an easy thing that will be natural to you if you haven't practiced this. So if you're just getting started, it's quite possible that it will feel alien and maybe even just really uncomfortable to sit there and really think about the details of writing a TLA Plus spec. But it's a good exercise. It will really help you deepen your understanding of your system. So there are numerous resources for learning TLA Plus. There is a homepage, and the content there is mostly by Leslie Lamport, the creator of TLA Plus. There's a book by Mr. Wayne, really good book. Check it out. Video was inspired by an article by Jack Van Lightly, who also has a pretty good collection of specs, TLA Plus specs on GitHub that you should perhaps check out. Yeah, I think we've covered everything that I will say will be a very, very, very introductory look at thinking about using TLA Plus for system modeling. And my hope is that with this type of content, people are more interested in exploring the use of formal methods, especially again with the advent of AI agents and all that. It's a good way to really think about your system, because once you do that, you can feel more, I suppose, liberal in terms of how much of the actual coding and implementation detail that you delegate to these AI coding agents. All right, so I hope this was enlightening for you, and do like and subscribe, and I'll see you in the next one. And Happy New Year again. I hope this is the year that you investigate the use of formal methods. All right, see you around.